Welcome to Space Dreams documentary, where the universe slows down and every color of light tells a different secret. Tonight's journey drifts through radio whispers, infrared warmth, visible glow, and the quiet fire of X-rays. Each wavelength reveals a hidden layer of cosmic structure, from thin shock rims to gentle gravitational arcs. If this kind of deep, peaceful science story is your space to unwind, please like the video, subscribe to the channel, and turn on notifications so the next voyage finds you. What does a sky become when light is counted beyond the visible band? It becomes a layered record of how matter blocks light. Matter also scatters light and remakes it as glow. In a quiet spiral arm, a cold filament of gas stretches like a long ribbon. Its center looks like a deep lane of shadow. Along the sides, brightness rises in a smooth gradient. The edge is thinner. The middle is thicker. In one band, that thickness hides nearly everything. In another band, signals pass with little loss. In another, the same filament turns into a faint warmth. A single place becomes several kinds of information at once. The first key is wavelength, the spacing between peaks in a traveling wave. A long wavelength tends to ignore small obstacles. A short wavelength tends to notice them. A common radio wave can be about 2 million times longer than a common visible wave. The difference is like a mountain ridge compared to a small pebble. In that contrast, a quiet rule appears. Matter does not hide from all light in the same way. A thin haze of dust can erase one band and spare another. The filament keeps its dark spine in visible light, yet its bulk still holds signals that cross it with little change. Along the rim, the boundary between dense and thin gas turns into a contour. It is a slow curve in brightness. The curve is not decoration. It is a clue that thickness varies from edge to core. A second scene settles beside it. A broader cloud surrounds the filament like a dim veil. The veil is uneven. It has wisps and knots. Some parts look like stacked layers of smoke fading into clear air. The scene holds stillness, yet it also contains direction because gradients point to structure. Another key is opacity, the ease with which light moves through material. Opacity is how strongly material blocks light at a wavelength. When grains are close in size to a wavelength, scattering grows strong. Light changes direction and loses a clean path. Shorter waves are scattered more easily by fine dust than longer ones. The scattered light gathers near the surface. The interior stays muted. A boundary appears like a pale skin over a darker core. That skin is not a surface like rock. It is a zone where light changes direction many times. The glow at the edge does not prove the edges hotter. It often proves the edges easier to reach. Some light escapes from shallow layers. Deeper layers remain hidden. In another band, the same filament changes character. Infrared light does not care as much about the fine dust that ruins shorter waves. It threads through layers that look sealed in the visible band. A third scene takes shape. The dark spine is no longer a simple lane. It becomes a soft ridge in brightness. It is smooth at the center. It is fainter at the sides. It resembles a dune seen from above. The ridge does not shift like sand, yet the shape hints at compression and layering. Thickness becomes something that can be traced. Another quiet rule arrives. Darkness in one band can be brightness in another. The reason is not magic. It is physics of interaction. The same material both blocks and glows. A second core idea joins in. Temperature sets which wavelengths a warm object emits most strongly. Temperature sets which wavelengths a warm object emits most strongly. Cooler material tends to glow in longer wavelengths. Hotter material tends to glow in shorter wavelengths. Dust warmed by nearby radiation can shine in infrared, even when the region is dark in visible light. Gas heated to extreme temperatures can radiate in X-ray light. Such gas often sits in thin shells and sharp boundaries. It forms where flows collide and slow down. Even without any visible motion, the geometry can show it. A thin arc can trace a shock front. A softer interior can show cooling. A fourth scene forms as a quiet contrast. A faint bubble surrounds an emptier cavity. The bubble is brighter at its rim. The center is dim. The rim is a narrow ring of emission. It is a boundary where conditions change rapidly. The ring appears delicate, yet it can span distances far larger than the filament width. One small detail returns again and again. Boundaries matter, edges brighten, interiors hide, gradients reveal layering. These are not separate stories. They are the same story told by different wavelengths. The scale shifts outward. The filament is one structure among many across a galaxy. The same rules repeat across the disk. Dark lanes thread between brighter patches. Warm dust fills spiral arms as a diffuse sheen. Hot cavities appear as faint bubbles in higher energy light. The galaxy becomes a set of overlapping layers that do not align perfectly. Some layers track dust, some track hot gas, some track cold gas. The scale also shifts inward. Inside, the filament grains drift in spaces far smaller than a snowflake. Those grains control scattering. Molecules form and break apart in tiny pockets. Their large ribbon depends on small particles. This dependence sets a quiet limit. No single band delivers a full truth. Some bands lose direction because long waves cannot trace a boundary much smaller than their own scale. Fine structure blurs into broader patches. Some bands lose depth because opacity hides interiors behind surface layers. Some bands lose completeness because the strongest emission comes only from the hottest or the warmest material. The result is a series of partial views. Each view is honest within its own rules. Each view is incomplete by itself. Another scene returns to the filament again. The rim looks sharper in one band and softer in another. The same curve changes character. In one view, it resembles a clean shoreline. In another, it resembles fog at the edge of a valley. That shift is an instruction. Light behaves as a probe whose reach depends on wavelength. A signal would cross one region and fail in the next. An object would glow in one band and stay silent in another. This is the calm power of the spectrum. It does not add drama. It adds constraint. When a band is blocked, the blocking itself becomes a measurement of thickness and grain size. When a band escapes, the escape becomes a measure of transparency. When a band glows, the glow becomes a measure of temperature and density. The same filament can therefore reveal both what is present and what cannot be seen directly. The frame becomes stable. The sky is not one picture. It is a set of layers that share the same space. The next step follows the longest waves first. Radio light carries the quiet imprint of broad structure. It moves through dust that silences shorter waves. It begins the journey into signals that persist where other light softens and fades. Radio light arrives as patience in waveform. It carries the outline of structures that visible light can lose behind dust. In a quiet spiral galaxy, the luminous disk is a thin band. Above and below that band, a faint radio glow spreads into two broad lobes. The lobes curve like soft wings made of dim haze. Their edges fade through a smooth gradient into deeper darkness. A few narrow filaments lace the glow. Each filament bends in slow arcs. Each arc hints at an ordering that cannot be seen directly. A small unlock settles in place. Radio often describes shape before it describes surface. The shape can come from motion and from fields that guide motion. In that region, the long waves pass through dusty lanes with little change. The same lanes stay heavy and opaque in visible light. The radio glow does not remove the dust. It simply avoids the trap the dust sets for shorter waves. Another scene forms closer to the disk. The spiral arms look like faint ribbons. Their brightness is not uniform. It thickens in patches. It thins between patches. The transitions are soft like layers of silt settling in slow water. This quiet patchiness carries a second unlock. Radio brightness can mark where energetic particles travel. It can also mark where cold gas gathers. The two stories overlap in space but differ in origin. Synchrotron emission is light from fast charges spiraling in magnetic fields. A drifting seed can circle inside a gentle eddy and keep returning to the same curve. A bright thread in the radio band can resemble that repeated circling. The importance is simple. The glow shows where magnetized regions hold fast motion. The motion does not need to be seen as a streak. The light carries the signature of the spiral path. A charged particle curves around a field line in a tight helix. The helix is small compared to the structures it fills. The large lobes can span the space around a galaxy, yet the glow begins in curves smaller than a grain of dust. This scale shift remains calm. The smallest loop and the widest halo belong to the same physics. In one place, the radio filaments look like braided strands. Their thickness varies along their length. Some parts narrow to a thread, some parts swell into a wider ribbon. The boundary between bright and faint is not sharp. It is a gradient that suggests a spread of energies. When the fast particles lose energy, the glow softens. When fresh particles arrive, the glow strengthens. A third scene arrives in a darker lane that crosses the disk. The lane stays dark in visible light. In radio, it becomes a subtle ridge. It is not bright like the lobes. It is smoother and broader. The ridge follows the lane's path as if tracing the lane from within. Another unlock becomes available. Cold material can announce itself without shining in visible light. It can do so through a single radio color that comes from hydrogen. The 21 centimeter line is a radio tone from neutral hydrogen. 21 centimeters is about the length of a pine cone. The tone is not created by heat in the usual sense. It comes from a quiet change inside the hydrogen atom. The change is rare for any single atom. The atoms are so numerous that the combined signal becomes steady. The ridge across the disk is not a wall. It is a layered sheet. The sheet is thicker in the spiral arms. It is thinner between them. The thickness is a physical detail that matters. It sets how much hydrogen lies along a path. It also sets how much the signal is blended by depth. Another visual anchor moves even closer. A ring-like band of hydrogen wraps the galaxy. The band is not a perfect circle. It is slightly warped. Its upper edge lifts above the disk in one quadrant. Its lower edge dips in the opposite quadrant. The warping is gentle, like a soft bend in a leaf stem. The bend reveals that gravity and motion are not perfectly flat. The radio tone carries motion as well as presence. When gas on one side approaches, the tone shifts slightly. When gas on the other side recedes, the shift goes the other way. The result is a calm clue. Rotation can be traced without seeing individual clouds. The entire disk can be weighed in a broad sense, yet a limit arrives with the same softness. At long wavelengths, fine boundaries blur together. A small knot can merge into its surroundings. The wave cannot outline edges much smaller than its own scale. Another limit follows from geometry. Along any line through a galaxy, many layers overlap. Front and back blend into one measurement. The depth cannot be separated cleanly from a single radio view. A bright ridge can mean dense gas. It can also mean a long path through moderate gas. The inference is indirect. It depends on assumptions about thickness and filling. This does not weaken the view. It simply states what the view can and cannot unlock. Another payoff settles in. When radio and visible disagree, the disagreement is information. A dark lane in visible light can be a rich reservoir in radio. A bright star field can be quiet in hydrogen. The contrast reveals that brightness is not the same as mass. The galaxy becomes less like a picture and more like a set of layers in motion. The lobes above and below the disk remain in place as a slow frame. They suggest that magnetic structure extends beyond the bright spiral arms. They also suggest that fast particles travel far from their birthplaces. The filaments within the lobes show that this travel is not random. It follows curved paths that keep their coherence over great distances. The hydrogen ridge within the disk provides a different calm anchor. It shows where the raw material of future change rests. It shows where spiral arms compress the gas into thicker sheets. It shows where interarm regions thin into quieter layers. From the smallest atomic change to the broad halo radiolight holds both presence and motion. The next step shortens the wavelength while keeping the calm. Microwaves carry an even older glow that fills the spaces between galaxies. Microwaves linger as a calm afterglow that seems to come from every direction at once. They preserve a snapshot from an early time when space stops acting like a dense fog for light. A wide darkness holds a faint even sheen. The sheen has no obvious center. It wraps around like a thin film of pearl grey haze. In that film, brightness stays nearly uniform. Small speckles break the uniformity. The speckles form a soft marbling. No single patch dominates. The pattern looks quiet, yet it carries a record of long change. The cosmic microwave background is ancient light cooled into microwaves. It resembles a thin layer of warmth spread across the whole sky. It resembles the faint chill that remains after water becomes ice. It matters because it marks when light begins to travel freely over cosmic distances. The glow is extremely cold. It sits about 3 degrees above absolute zero, like water held just above the point where it would freeze. That number does not describe a place. It describes a condition shared by nearly all directions. At this distance, the glow behaves less like a single spark and more like a background tone. A new physical detail emerges when the marbling is followed carefully. Some patches blend into their neighbours through smooth gradients. Some boundaries are slightly sharper. Those boundaries are not edges of objects. They are gentle steps in density from long ago. Even a small step changes how tightly early matter holds its heat. A small step changes how bright a patch becomes in microwaves. The sky carries a map of tiny differences that later grow into larger structures. A second scene settles in. The marbling drifts into broad bands that curl and fade. The bands look like faint eddies in a river pool after fine clay has dispersed. The eddies do not swirl in time here. They are frozen in the light itself. That frozen quality points to a single moment. Last scattering is the moment matter stops trapping light. Before that moment, light bounces again and again in a dense mixture. After that moment, light streams outward and rarely meets anything dense enough to turn it back. The early mixture thins as the universe expands. It cools as it expands. One calm rule appears. As space stretches, each wave stretches with it. Old hot light slides into the microwave band. The scene can be held like a clear sheet of ice that traps the shape of ripples beneath its surface. The ripples are not moving anymore. They are preserved as shape. They matter because they reveal conditions at the time the light last touches dense matter. Another visual anchor arrives at a different scale. Instead of filaments or lobes, the geometry becomes a shell. Every direction points to a distant layer where microwaves last scatter. The layer is not a wall, it is a thin region with depth. Its thickness is small compared with its distance. This is a gentle shift from near structures to a far boundary. The filament of a spiral arm becomes irrelevant here. An entire galaxy becomes a tiny detail on top of the older glow. Anisotropy is a tiny difference in brightness across directions. It is subtle enough that the background still feels smooth. It is like a slight breeze that only tilts the surface of a pond by a breath. It is like a barely visible grain pattern in stone when the stone is turned in low light. It matters because those tiny differences encode the earliest seeds of later clustering. The marbling is not random noise. It follows a distribution that reflects pressure waves in the early mixture. Those waves leave rings and arcs within the pattern itself. The rings are not seen as perfect circles in a single glance. They appear when many directions are compared. The idea stays gentle. The early universe supports a kind of sound. It is carried by radiation and matter together. Where compression is slightly higher, the glow is slightly different. Where it is slightly lower, the glow shifts the other way. A third scene forms with more texture. Some regions show a faint smudge that stretches longer than it is wide. The smudge tapers at both ends. It resembles a distant cloud band seen through thin haze. The taper hints at a gradient in density. That gradient hints at a flow of heat in the early mixture. From this small smudge, a larger scale becomes imaginable without urgency. Over billions of years, gravity amplifies small differences. Regions that begin slightly denser tend to gather more material. Regions that begin slightly thinner tend to empty. The microwave pattern is the quiet beginning of that contrast. A limit appears with the same softness. Microwave light is uniform enough that many different histories can still fit the same smooth glow. The average temperature alone cannot distinguish them. The fine pattern helps, but it is extremely faint. A measurement would be swamped if other emissions are not separated from it. Warm dust in galaxies also glows at nearby wavelengths. Fast particles also produce low-frequency haze. Those foreground layers overlap the older signal along every line of sight. The separation is not direct. It relies on assumptions about how different sources change with wavelength. Another limit comes from resolution. Any map of the sky blurs features smaller than the available sharpness. Small-scale ripples merge into a smoother background. The result can hide the very smallest seeds. Still, a calm advantage remains. The microwave background is everywhere. It does not depend on rare events. It does not prefer crowded regions. It offers a uniform reference layer behind later structures. A final scene settles toward rest. The pearl grey shell remains with marbling so delicate it nearly disappears. In that faintness, the universe appears both young and old at once. The signal comes from a time long before galaxies have clear shapes. It arrives in the present as a steady field of gentle variation. From that oldest glow, the path can move forward in time again. The next step follows warmer dust as it begins to glow in far infrared light. Cold dust seems silent until far infrared light begins to show it. It reveals hidden matter by turning absorbed starlight into a slow glow. In a spiral arm, a dim ribbon curves across darkness. The ribbon has a clean outer edge. It fades inward through a long gradient. Small clumps sit along the ribbon like dew along a spider thread. Each clump is round and slightly brighter at its rim. The first unlock is simple. The glow tracks dust even where visible light is swallowed. Thermal emission is light released by warmth. A grain absorbs energy. It shares that energy among vibrations in its lattice. It releases new light at longer wavelengths. The process is quiet and steady. It does not need sparks or flashes. In that region, the grains remain cold. They sit at about 20 degrees above absolute zero, like stone kept in permanent shadow. That coldness pushes their glow into far infrared and beyond. A second scene forms inside the same arm. A dark lane crosses the ribbon in visible light. In far infrared, the lane becomes a smooth ridge of brightness. The ridge is thickest at the center. It thins toward both sides. The shape shows layering. Light behaves as if the lane is both curtain and afterglow. The dust blocks shorter waves. The same dust becomes the source of longer waves. The second unlock follows at once. Darkness in one band can be a mass map in another. Opacity becomes the hinge for that change. Opacity is the ease with which light passes through material. When opacity is high, light is trapped in surface layers. When opacity is low, light slips through deeper columns. Fine grains scatter short waves more strongly. Long waves pass with less deflection. This difference makes edges appear. A bright skin can wrap a darker core. The skin is not hotter by default. It is simply where light escapes. Another scene appears when a dense clump sits before a diffuse sheet. In a shorter far infrared band, the clump can look dimmer at its core. It makes a shallow shadow because opacity rises with thickness. In a longer band, the same clump can look brighter and smoother. The contrast unlocks a quiet depth cue. It hints that the center is so dense that its own glow is muffled. This effect is gentle self-absorption. It is warmth hidden behind warmth. A third scene settles around a hollow cavity in a cloud. The cavity is dim in far infrared. Its boundary forms a thin ring of brighter glow. The ring is uneven. It thickens where the surrounding material is denser. It thins where the gas is more rare. The ring shows a temperature gradient. The outer side is cooler and fainter. The inner side is warmer and brighter. Another unlock arrives in the curve of that rim. Far infrared can separate warm surfaces from cold interiors. Temperature becomes a guide without showing flames. Slightly warmer dust shifts its glow to shorter infrared light. Slightly cooler dust shifts its glow to longer submillimeter light. In submillimeter light, the same ribbon looks heavier and smoother. The clumps gain wider halos. Their bright rims soften. Their centers become more prominent as bulk matters more than skin. The change offers a quiet key. Longer waves can emphasize cold columns that shorter waves only graze. The shift is gentle. It is like ash that looks dark yet still holds a faint warmth signature. Within a single clump, warmth and depth compete. The outer layers warm first. They cool fast compared with the age of the cloud. The interior stays colder for much longer. A calm scale shift appears. A grain smaller than a speck shapes the brightness of a clump. A chain of clumps shapes the look of a spiral arm. A spiral arm shapes the glow of a galaxy. A fourth scene moves outward across the whole disk. The spiral pattern becomes a broad set of luminous bands. Between the bands, the glow drops into quieter lanes. The lanes are not empty. They are simply thinner in dust. The contrast offers another unlock. Far infrared measures reservoirs, not just the brightest sites. It traces where material can later form dense knots. It also traces where material has already been stirred into diffuse sheets. A fifth scene drifts through the disk like a low, even mist. The mist is patchy. It gathers into smooth sheets around the arms. It thins into a faint veil between them. At this distance, a galaxy looks like layered weather seen from far above. Yet the layers are dust and gas, not air and water. That comparison opens another small certainty. A faint far-infrared background can exist even where stars look sparse. Dust can be heated by diluted starlight over long spans. It does not require a single bright source nearby. Yet a limit arrives with the same softness. The glow depends on both dust amount and dust temperature. A brighter patch can mean more grains. It can also mean slightly warmer grains. Without several wavelengths, the two causes can blend. Another limit comes from grain properties. Grains differ in size and composition. Those differences change how efficiently they emit. A model must assume a typical mix. The inference remains indirect. A further limit comes from depth along a path. Many clouds can overlap in one direction. Their glows add together into one smooth patch. The layers cannot be separated cleanly from a single view. Sharp structure is also limited by resolution. A map would blur a narrow filament into a wider band. Small clumps can merge into one soft hill of light. Even with limits, the view stays powerful. Where the far infrared glow is strong, dust is present in bulk. Where dust is present, gas is often present as well. The ratio is not fixed everywhere. It varies with environment. Still, the glow offers a steady proxy for hidden mass. A final scene returns to the ribbon in the spiral arm. The dew-like clumps remain in place along the curve. Their rims stay gently bright. Their centers stay dimmer. Layering is visible as a soft depth cue. The band feels calm and heavy at once. From this cold glow, the spectrum can move toward warmer dust. Nearer to forming stars, infrared light begins to show enclosed heat in tighter cocoons. Near-infrared light turns some dark clouds into gentle maps of hidden structure. It does so because longer waves slip through dust that traps shorter waves. In a quiet region of cold gas, a rounded globule hangs like a dense island in a thinner haze. Its edge is softly bright. The center is darker, as if light sinks into it and does not return. Across the middle, a narrow lane appears straight compared with the globule's curve. The lane divides the center into two dim halves. Above and below that lane, two faint lobes glow. Each lobe has a brighter rim and a softer interior fade. The rims trace a shallow bowl shape. The interior looks like mist lit from within. A quiet fact becomes visible. The near-infrared view does not erase dust. It shows where dust becomes thin enough for light to leak through. The divided lobes and the thin dark lane imply a flattened layer inside the globule. The geometry is carried by light alone. Near-infrared means wavelengths of about 0.002 of a millimeter, about the width of a fine dust grain. When the wave and the grain are similar in scale, the grain becomes an efficient gatekeeper. Some light is absorbed. Some light is scattered into new directions. Extinction is the combined dimming by absorption and scattering. It resembles sea ice that allows a deep swell to pass while stopping small ripples at the edge. In visible light, the ripples are the main signal. In near-infrared, the deeper swell becomes easier to follow. This matters because the thickest regions can be crossed by some bands but not by others. Another scene settles along the globule's rim. A thin crescent brightens where the curve meets the background glow. The crescent is narrow and clean, then it fades outward into the haze. The brightness changes through a smooth gradient. That gradient is a physical detail tied to depth. A longer path through dust means more chances for scattering. More scattering means a brighter skin. The center stays darker because the path is thick enough to dim even near-infrared light. Brightness at the rim can mark thickness rather than heat. A third scene forms inside one lobe. Fine striations run outward like brushed fibers. Each striation is faint. Together they suggest layered density. Light behaves as if it is grazing along uneven sheets. Where a sheet is tilted, the glow strengthens. Where it turns away, the glow weakens. The effect is gentle. It shows structure without any need for sharp edges. Near-infrared can reveal gradients that visible light turns into a single black patch. Now the scale shifts inward. Within the globule, dust grains drift among molecules at separations far smaller than a grain's width. Those grains control which wavelengths pass. A small change in grain size can change the balance between absorption and scattering. The glow is therefore a proxy for a hidden population of particles, yet the scale also shifts outward. Many globules can sit along a filament. Many filaments can braid through a spiral arm. The same rules of extinction and leakage repeat across distances that span a galaxy. In that broader view, near-infrared light becomes a bridge between maps of cold dust and maps of visible starlight. A fourth scene arrives around the central lane. The lane is not perfectly uniform. It thickens toward one end and thins toward the other. The transition is gradual. Where it thickens, the adjacent lobe dims. Where it thins, the lobe brightens. The pattern points to a simple cause. A thicker midplane blocks more light and scatters more away from the line of sight. A thinner midplane allows a clearer escape route. The two lobes therefore encode a three-dimensional shape. One lobe can be slightly nearer, the other can be slightly farther. The difference does not need to be dramatic to be readable. Another gentle clue appears in colour, light that passes through more dust shifts toward longer wavelengths. Shorter components are removed first. The result is a redder tone in the surviving light. This is not a change in the source itself. It is a filter made by dust. Redder near-infrared patches can mark deeper paths even when no surface is visible. A fifth scene forms when the globule is imagined in two infrared bands. In the shorter near-infrared band, the lobes look sharper. In the longer near-infrared band, the same lobes look smoother and broader. The rims soften. The interior fills in. This change hints at a second contribution to the glow. Some light is scattered starlight from outside the globule. Some light is thermal emission from dust warmed inside. The two contributions mix, but they shift with wavelength. Thermal emission rises as dust becomes warmer. Scattered light weakens as the background illumination is extinguished. Comparing bands can separate glow that is reflected from glow that is re-emitted as heat. Now a limit arrives in a calm form. Near-infrared still cannot see through the densest cores. Where extinction is extreme, even these waves are reduced to a faint whisper. The inner source can be hidden behind a veil that remains opaque. Another limit follows from interpretation. A bright patch can mean less dust along the path. It can also mean warmer dust. Without multiple wavelengths, those causes can be confused. A further limit comes from overlap. Several layers can lie along one direction. Their glows add together into one smooth lobe. Depth is then inferred, not directly measured. Even the thin dark lane can be misleading if separate layers align by chance. These limits do not remove meaning. They define the boundary of what can be claimed. Within those boundaries, near-infrared still offers a calm advantage. It retains finer detail than far-infrared. It also penetrates dust better than visible light. The two-lobe geometry remains readable at smaller scales. The rim gradient remains measurable across wider regions. A final scene settles back onto the globule as a whole. The crescent rim holds its gentle arc. The twin lobes keep their bowl-like edges. The dark lane stays as a thin belt of shadow. The entire structure looks like a layered shell with a hidden interior. From this middle band of the spectrum, the path can move toward visible light where surfaces and sharp shadows return. The next step follows the familiar band that dust often interrupts yet still illuminates boundaries with clarity. Visible light feels like a narrow doorway between longer warmth and shorter bite. It draws sharp boundaries and clean shadows, yet it often shows only the outer skin of dusty regions. In a bright cloud of glowing gas, a dark pillar rises as a silhouette. The pillar has a rounded head. Its sides taper into a thin trunk. Along the rim, a bright edge forms a tight arc. The arc is brightest where the curvature is steepest. It fades through a smooth gradient into the surrounding glow. A quiet cause becomes clear. Dust blocks visible light so efficiently that shape is revealed by absence. The pillar is not empty. It is simply opaque in this band. Visible wavelengths are about 0.005 of a millimeter, about 1,000 times smaller than a grain of sand. At that scale, fine dust becomes an effective filter. The filter does not need to be thick to work. A thin layer can dim the background strongly. The result is a landscape of contrast. Bright sheets press against dark lanes. Edges become information. In that region, the glowing gas itself adds light. Ionized gas means atoms missing one or more electrons. The missing electrons return under the right conditions. The return releases visible light in narrow colors. The process resembles a bell that rings only on certain notes. The notes matter because they trace where gas is energized and where it cools. In the bright cloud, the rim of the pillar glows because it faces the incoming radiation. The rim is a boundary zone. The boundary is thin compared with the pillar width. It is like the crust on cooling lava. It marks where conditions change quickly with depth. The interior stays dark because dust and denser gas shield it. A second scene forms beside the pillar. A long ridge of glow curves like a wave crest. In front of that ridge, a thinner veil of dust hangs in the foreground. The veil is not fully black. It is a soft grey sheet. Its texture looks like layered gauze. The sheet is patchy. Some patches thin into near transparency. Some patches thicken into deeper shade. The shade is not uniform because dust is clumped. This offers a gentle certainty. Visible light is excellent at tracing uneven layers. Small changes in thickness appear as large changes in brightness. A third scene settles farther out. A dense cluster of stars fills a region with tiny points of light. The points are not all the same color. Some lean toward blue-white, some lean toward warm gold. Across the cluster, the colors shift subtly. Near one edge, many points look redder. The redder region lies behind a faint dust veil. The veil is almost invisible as a shape. It reveals itself by changing color more than by blocking all light. A simple rule follows. Dust removes more blue light than red light. Light that passes through dust becomes redder. This reddening is not a property of the stars. It is a property of the path. Color can therefore map dust even when no clear shadow exists. In that same cluster, brightness alone becomes unreliable. A dim point can be far away. It can also be nearby and partly blocked. Visible light brings detail, but it can mix causes. The scale shifts inward again. Dust grains smaller than a speck shape the color of a star field. The scale shifts outward again. Whole spiral arms of a galaxy can be traced by lanes of dark dust. A fourth scene appears in a distant disk galaxy. A bright central bulge glows softly. Across that bulge, a dark lane slices through like a thin band of ink. The lane has ragged edges. It breaks into smaller filaments toward the outskirts. Each filament frays into finer threads. The fraying shows turbulence and layering in the dust. The lane is not flat in appearance. Its top edge is sharper than its bottom edge. This asymmetry hints at depth. One side is nearer along the line of sight. The nearer side blocks more of the bulge. A calm payoff settles in place. Even without motion, a dust lane can suggest which side of a disk tilts toward the observer. Geometry becomes readable through shadow. Yet another limit arrives quietly. Shadows alone cannot reveal how much dust is present in total. A thick lane and a thin lane can both look black once opacity is high. When a surface is fully opaque, deeper layers become invisible in this band. The measurement saturates. The map becomes a map of surfaces. A fifth scene forms in a reflection nebula. A faint blue haze surrounds a dark clump. The haze is brightest along a curved arc that faces a brighter background. It fades outward into transparency. The arc looks like a crescent of smoke lit from the side. This is scattering made visible. Scattering redirects light rather than creating it. Blue light scatters more strongly than red light in many fine dust mixtures. The haze therefore leans blue. The clump remains dark because the interior does not let light pass. The combination of glow and shadow is a depth cue. It shows a bright background, a scattering layer, and an opaque core. Another calm certainty appears. Visible light can show both blocking and scattering in the same scene. The balance between them depends on grain size and density. A sixth scene arrives in a thin expanding shell around a star in a late stage. The shell forms a ring-like structure. Its ring is brighter on the limb and dimmer toward the center. The brightness changes because the path through the shell is longer along the rim. The rim is a boundary traced by geometry. The center is not empty. It is simply a shorter path through emitting material. This limb brightening explains why some shells look like rings. The rule does not require a hollow ring. It requires a thin layer seen in projection. The visible band is well suited to this kind of structure. It resolves sharp filaments and crisp arcs. It shows where emission is confined to thin fronts. It also shows where dust cuts a clean silhouette against background light. A limit follows from the same strength. Fine detail can distract from the full energy budget. Bright visible emission can come from a small amount of hot gas. A larger mass of cold material can remain unseen. Another limit follows from distance. Farther regions appear dimmer even if they are intrinsically similar. Brightness mixes with geometry and obscuration. Without other wavelengths, the path length and the true luminosity can be hard to separate. A final limit follows from indirect inference. Visible colors can suggest temperature and dust, but many combinations can produce similar colors. A model must assume dust properties and intrinsic spectra. The view remains powerful within those assumptions. It offers crisp edges and clean gradients. It reveals where fronts are sharp and where layers overlap. It also teaches humility about interiors. The next band moves shorter. Ultraviolet light highlights harsher radiation and finer boundary zones where visible light begins to soften. Ultraviolet light appears where ordinary glow gives way to sharper boundaries. It highlights surfaces and transition layers because the shortest waves are absorbed quickly by dust and neutral gas. In a wide cloud, a hollow cavity opens like a dark bowl. Around its rim, a thin ultraviolet skin shines. The skin is not smooth, it is scalloped. Small protrusions rise from the rim like rounded fingers. Each finger has a bright edge. Each edge fades into a softer interior gradient. At this distance, light behaves as a tracer of the last layer it can reach. A quiet unlock settles in place. Ultraviolet often marks the boundary where energetic radiation meets sheltered material. That boundary carries shape more than depth. The shortest waves do not wander far into dense regions. They touch what is exposed. They leave interiors quiet. Ultraviolet is about 1/10 the wavelength of visible light, like a narrow crease beside a broad fold. That shorter scale changes how dust and gas interact with the wave. Fine grains and neutral atoms become strong gates. The result is a map of surfaces and rims. Another scene settles near one protrusion on the cavity edge. The tip is brighter than the base. The base looks smeared as if the glow spreads along the rim before it fades. The brightness does not mean the tip is larger. It means the tip faces more directly into the energetic field. Geometry becomes a kind of compass. A surface angled toward the incoming radiation responds more strongly. A surface turned away responds less. This is not a motion that can be watched. It is a pattern that can be read. Photoionization is atoms losing electrons after absorbing energetic light. The loss happens where ultraviolet reaches. It happens first at the surface of dense gas. It is like fine frost that forms only on exposed ridges, while sheltered hollows stay bare. The frost is not cold here. The similarity is selection. Only exposed surfaces show the effect. Two examples follow at once. A dense knot at the rim glows on its outer face and stays dark behind it. A thinner sheet glows more evenly because light reaches deeper through it. The importance is simple. Ultraviolet brightness traces where radiation meets matter. It also traces the angle and roughness of that meeting. Another small unlock emerges when the rim is followed from end to end. Where the rim is smooth, the glow is continuous. Where the rim is rough, the glow breaks into beads and arcs. The beads sit at the crests of density variations. The arcs wrap around indentations. The pattern suggests that the rim is layered. It is not a single wall. It is a stack of sheets with uneven thickness. At this distance, a thin sheet can glow strongly if it is fully exposed. A thick sheet can glow only on its outer skin. A third scene forms deeper in the cavity. The interior is dim in ultraviolet light. Yet faint streaks cross it like wisps of smoke. The streaks curve gently. They thicken near the rim and thin toward the center. Each streak is a trace of scattered light. Dust can redirect ultraviolet light. The scattered component does not travel as a clean beam. It spreads into a soft haze. This provides a calm payoff. Even when ultraviolet cannot penetrate a dense wall, it can still outline the cavity through scattering from its edges. The cavity becomes legible as a shape rather than a depth. The physical detail remains consistent. Bright rims, soft gradients, dark interiors, sharp changes over small distances. Those are signatures of a boundary-dominated band. Now the scale shifts inward. The entire effect begins with electrons bound to atoms. A single absorbed photon can free one electron. That microscopic change alters how the gas emits. The gas can later return an electron to a bound state. During that return, it releases light in specific bands. Those bands can include ultraviolet. The process is not a continuous spectrum. It is a set of favored colors. The favored colors act like marks in a long code. The code does not need to be read in full here. The key is that ultraviolet can trace both the cause and part of the response. It traces the presence of energetic radiation. It also traces the thin zones where gas becomes ionized and then cools. The scale shifts outward again. A boundary only a small fraction of a cloud's width can wrap around a cavity that spans vast distances. The same thinness holds at many sizes. Small knots show bright skins. Large shells show bright limbs. Another scene settles on a separate structure nearby. A long arc curves across darkness. The arc is bright at its crest. It is dimmer along its wings. The arc has a narrow leading edge and a wider trailing fade. The leading edge indicates a front. The trailing fade indicates a zone where conditions relax. The arc is an ionization front. It is the moving boundary between ionized gas and neutral gas. The front is not a hard wall. It is a region where the balance changes rapidly with depth. The balance depends on how many energetic photons arrive and how much neutral material absorbs them. Another unlock lands gently. The front's thickness reveals a competition between radiation and density. In thinner gas, ultraviolet penetrates farther and the transition spreads out. In denser gas, absorption is stronger and the transition becomes thinner. The front, therefore, carries a clue about how tightly matter is packed. Yet the inference is indirect. It relies on assumptions about composition and dust content. A limit appears without drama. Ultraviolet is easily extinguished by dust. It is also absorbed by neutral gas along the path. A region can look faint because it is intrinsically faint. It can also look faint because intervening material removes the light. The band is therefore sensitive but not always transparent. Another limit follows from projection. Rims can appear brighter simply because the path through a thin shell is longer at the limb. A curved sheet can look like a sharp arc even when it's broad in depth. Without other wavelengths, shell thickness and true density can be confused. Resolution adds a further constraint. Fine ripples along a front can blur into one smooth curve. Small fingers can merge into one bead of light. The map then loses the smallest roughness that holds information about instabilities and layering. Still, ultraviolet offers distinct promise. It focuses attention on the interface between radiation and matter. It highlights where gas is being reshaped. It shows where dense clumps resist that reshaping by casting compact shadows. A final scene returns to the scalloped rim of the cavity. The protrusions stand in a quiet row. Each keeps its bright edge. Each keeps its softer fade. Behind each, a faint shadow stretches into the cavity like a long smudge. The shadows are not empty. They are sheltered columns where ultraviolet fails to reach. The pattern holds a calm conclusion. Ultraviolet does not describe the whole cloud. It describes the exposed frontier. From that frontier, the spectrum can shift to higher energies. X-ray light reveals even hotter gas and thinner shells where shocks and collisions dominate. X-ray light appears when matter becomes too hot for familiar colors. It traces gas that is heated by shocks and compression into a thin, luminous plasma. In a wide galaxy cluster, a pale oval haze fills the space between galaxies. The center is brighter. The outer regions fade through a long gradient into darkness. Two dim cavities sit off-center like pressed hollows. Around them a faint ring spreads as a gentle ripple. The first unlock arrives quietly. X-rays often come from empty-looking space because that space is filled with hot, thin gas. Plasma is gas with electrons freed from atoms. The freed electrons move among ions like grains in a slow storm. When the gas is heated enough, atoms lose many electrons and stop making ordinary visible lines. The light shifts upward in energy and becomes X-rays. In that cluster haze, the temperature reaches about 10 million degrees, like air turned so hot it would no longer behave as a normal flame color. At this distance, that heat does not look like glare. It looks like a smooth fog of high-energy light. The fog is thicker toward the center because density rises there. The rise is seen as a brightness gradient. The gradient is a physical detail that matters. It reveals how gas is layered inside a gravitational bowl. A second scene forms at the edge of the oval haze. A thin rim brightens into a partial arc. Just inside the arc, the haze is slightly dimmer. Just outside, it is fainter still. The arc is a shock front. A shock front is a thin boundary where gas is suddenly compressed and heated. It resembles an ocean swell that steepens into a breaking edge, then leaves calmer water behind it. The edge is not a solid wall. It is a rapid change in pressure and temperature. The unlock is immediate. Where the arc appears, energy is being converted from bulk motion into heat. The arc's curvature hints at the shape of the disturbance that drives it. The gas responds by forming a thin, bright shell. The shell is bright at the limb because the path through the thin layer is longer there. A third scene settles closer to the cluster center. The two cavities remain dim. Their outlines are smooth and slightly elongated. Around each cavity, a brighter rim forms a rounded border. The border is not perfectly even. It is thicker at one end and thinner at the other. The border shows that the surrounding gas is being pushed aside. The cavity itself emits little X-ray light because its density is low. The rim emits more because gas piles up there. Another small payoff lands. X-rays can show pressure structures even when the driving cause is unseen. The cavities become readable as absences that shape their surroundings. The faint ring ripple around them becomes more meaningful. The ripple is a weak compression wave. It is a gentle pulse traveling through the hot atmosphere. Even a small pulse changes brightness because emission depends strongly on density. A slight increase in density raises the glow. A slight decrease dims it. A fourth scene appears as a set of delicate filaments near the center. The filaments are not as sharp as visible filaments in cold gas. They are broader and smoother. They curl like wisps in warm mist. Their edges blur into the background. The blurring is not only distance, it is also the nature of hot gas. Hot gas is thin. It does not form crisp dust shadows. Its structures are defined by pressure and flow. The flow is not seen directly. It is inferred from gradients and arcs. The main light mechanism in this hot gas is Bremsstrahlung, which means breaking radiation from electron deflection near ions. An electron passes near an ion and changes direction. The change produces a photon. Many electrons do this many times. The combined effect forms a smooth X-ray glow. The analogy is simple and new. It is like wind-driven sand that makes a soft hiss from countless tiny collisions, even when no single grain can be tracked. The hiss does not come from one loud event. It comes from the sum of small deflections. The importance is direct. A smooth X-ray spectrum can reveal temperature because hotter electrons produce higher energy photons more often. A fifth scene settles on a cooler patch embedded in the hot haze. The patch is slightly dimmer in X-rays. Its boundary is a smooth contour. The contour wraps like a soft lens shape. Around it the haze brightens. The patch is not empty. It is cooler and denser gas that emits fewer X-rays at the same energy band. The border is sometimes called a cold front. The name does not need drama. It is simply an interface between gas of different temperature and density. The interface is sharp compared with the broader gradients elsewhere. That sharpness offers a payoff. Hot gas can preserve layered structure because pressure balance can hold a boundary in place for long times. The boundary also reveals motion. A curved leading edge suggests the cooler patch is moving through hotter surroundings. The motion is slow on human scales and vast on cosmic scales. Over millions of years, such motions reshape the entire cluster atmosphere. Now the scale shifts inward. The X-ray glow begins with electrons and ions separated by distances smaller than a dust grain. The electrons carry heat. The ions carry mass. Their collisions set how quickly the gas can cool. If density is low, collisions are rare and cooling is slow. The gas can remain hot for very long times. The scale shifts outward again. The glowing haze spans distances so large that many galaxies could fit inside it. The same Bremsstrahlung process fills that immense volume with a continuous quiet radiance. Another unlock follows. Because the glow depends on density and temperature, it can hint at total mass. When hot gas sits in a gravitational bowl, its pressure gradient resists collapse. The steepness of the gradient hints at the strength of gravity. The inference is not perfect, yet it is informative. The brightness gradient becomes more than a picture. It becomes a map of how strongly the cluster holds its gas. A limit arrives gently. X-ray light is easily absorbed by cooler gas along the path. A modest column of intervening material can remove the softer X-rays first. The remaining spectrum looks harder. That can mimic higher temperature if absorption is not accounted for. Another limit follows from projection. The cluster is three-dimensional. The observed glow is a sum along a line of sight. Dense regions in front and behind add together. A hollow can be hidden if it is not aligned well. A sharp arc can appear even if the true boundary is a curved sheet at a different depth. Resolution adds a further constraint. Fine ripples can blur into a single smooth ring. Thin filaments can merge into broad haze. The smallest scales of turbulence and mixing can be lost. Another limit is physical. Very hot gas can be so thin that it emits only faintly. Large amounts of energy can be present with little light. X-rays then reveal structure but not the full energy content. These limits do not erase the value. They define what can be trusted. The cluster scene remains calm and legible within them. The cavities remain as quiet, dim ovals. Their rims remain as rounded borders. The shock arc remains as a thin, bright edge with a soft fade behind it. The ripple ring remains as a subtle contour that circles outward. Together, these features show how heat, pressure, and motion shape a hot atmosphere. From here, the spectrum can move to even shorter wavelengths. Gamma light will mark the most intense and brief high-energy processes where time itself becomes a key layer. Gamma light arrives like a brief glint that leaves almost no time for lingering. It marks the most compact and intense releases of radiant energy in the sky. In a deep black field, a single point flares and then collapses back into darkness. The flare is not a wide glow. It is a narrow cone that cuts through space like a seam of white fire. The cone has a crisp edge near its origin. Farther out, the edge softens into a faint halo. Around the cone, darkness remains undisturbed. A small unlock appears at once. A flash that brief implies a small source region. A signal that changes in about 1 second limits the size of its origin. 1 second is like the time for a raindrop to strike and the first ring to form. Light cannot coordinate a region larger than it can cross in that time. The flare can still be linked to huge events. The compactness does not mean small consequences. It means a tight engine and a tight channel. Gamma rays are the shortest and most energetic light. Their energy allows them to pass through some veils that stop softer bands. Their energy also makes them vulnerable to a different kind of loss. In a dense bath of radiation, a gamma photon can vanish into matter. Pair production turns light into an electron and positron pair. It is like a bright droplet splitting into 2 dark beads in midair. It is like a single wave crest breaking into 2 smaller crests. It matters because it can make a source opaque to its own light. The cone near the origin is therefore not only a shape, it is a constraint. If the interior is too crowded with photons, the gamma light cannot escape. A second scene settles around the flash. A faint shell forms where the cone meets thin gas. The shell is not bright in gamma light for long. It is a dim rim that expands. Its rim is brighter than its center. Its brightness fades through a gentle gradient. Limb brightening appears again, but in a new setting. The rim is a thin layer where motion slows. The interior is a lower density cavity behind it. Another unlock arrives. The flash can trigger a shock that keeps travelling after the gamma moment is gone. The shock becomes a messenger that lasts longer than the initial flare. The gamma light is the spark. The expanding shell is the footprint. The footprint can be broader than the spark by many orders of magnitude. A microscopic process starts the outflow. A macroscopic structure carries its aftermath. The scale shift remains calm. An electron's deflection can help create a photon. A shock front can span interstellar distances. Between them, motion ties everything together. The cone suggests beaming. Beaming is the focusing of emission into a narrow direction. It is like a lighthouse beam, but without any lamp or tower. It is like sunlight caught into a slit between moving clouds. The narrowing matters because it changes what is visible from afar. If the cone points away, the flash can be missed entirely. If the cone points closer to the line of sight, the flash can dominate the sky for a moment. This introduces a gentle limit of observation. The population of such events is biased by orientation. Many may occur without being seen in gamma light at all. Another scene forms with finer structure inside the flare itself. The brightness does not rise smoothly. It trembles in a few pulses. Each pulse has a sharp leading edge. Each pulse decays more slowly. The sequence resembles ripples that stack on top of each other after a stone falls. The ripples here are not water. They are changes in how energy is released and channeled. The pulse shape offers a small payoff. A sharp rise suggests a sudden onset in the engine or in the channel. A slower decay suggests cooling and thinning as material expands. Even without any direct image of the engine, timing becomes a form of geometry. The shortest variations place the tightest bounds. Longer variations hint at broader regions farther out. The pulses also point to another physical detail. The cone is not perfectly uniform. Its interior can contain layers. A fast core can be wrapped by a slower sheath. The boundary between core and sheath can be a zone of shear. Shear is a change in flow speed across a layer. It resembles wind that slides past a slower current and leaves a thin, wavering interface. Such interfaces can stir magnetic fields. They can accelerate particles. They can reshape emission without changing the overall direction of the cone. The gamma light therefore carries hints of internal layering. A fourth scene settles around the expanding shell again. Ahead of the shell, the medium is calm. Behind it, a faint wake trails in a widening cone. The wake is smoother than the initial flare. It is a slow fade rather than a pulse. The wake suggests that energy is now distributed across a larger region. Another small unlock follows. A brief gamma event can transition into longer-lived emission at lower energies. The spectrum slides as the shock cools and spreads. Gamma light is not always followed by a long tail. When it is, the tail becomes a ruler for the surrounding environment. Dense surroundings slow the shock faster. Thin surroundings let it travel farther before it dims. The shell rim brightness then reflects density outside the source. This is an indirect inference. It depends on a model of how shocks radiate. It also depends on assumptions about geometry. A narrow cone can mimic a wider one if the distance is uncertain. A fifth scene returns to the origin of the flare. The point is now dark, yet a faint oval glow remains around it for a time. The oval is not centered perfectly, it is slightly offset. The offset suggests motion of the surrounding gas or an uneven density field. The oval's leading edge is sharper, its trailing edge is softer. This asymmetry is another physical clue. The shock meets resistance unevenly. It thickens where density is higher. It thins where density is lower. At this distance, light behaves as a tracer of gradients rather than solid surfaces. Another limit arrives with the same softness. Gamma light is hard to localize precisely. The flash is brief. The cone is narrow. The sky background at these energies can be sparse in photons. A position can be constrained only roughly when the signal count is low. A second limit follows from absorption and transformation. Along a long path, the highest energy photons can be removed by interactions with ambient radiation fields. The observed spectrum can be softened by distance. The absence of very high energy photons can mean true absence. It can also mean loss during travel. The conclusion is cautious. Gamma light offers strong evidence of extreme conditions. It does not always reveal where the extreme conditions occur. It reveals that they occur. A sixth scene settles into a calm perspective. The flash is seen as a moment on a long timeline. The environment around it evolves over thousands and millions of years. The gamma moment lasts seconds. The shock's imprint can last far longer. The engine is compact and brief. The surroundings are broad and slow. This contrast becomes a quiet lesson in scale. The universe can concentrate energy in a tiny region, then distribute it across a vast volume. In that process, different wavelengths take turns as the best tracer. Gamma light captures the first instant. Other bands later carry the longer story. The next step moves from brief flashes to steadier sources. A persistent core can glow across many wavelengths, and the spectrum can be stacked into a single layered portrait. A single active galaxy can look calm in one band and intricate in another. Multi-wavelength light reveals that several physical layers coexist in the same core region. In a distant galaxy, the center is a compact glow surrounded by a thick oval ring. The ring is dark in visible light and bright in infrared light. Above and below the ring, two narrow lobes extend outward. Their tips fade into a broader radio haze. Near the center, a thin X-ray cusp appears like a bright needlepoint. The first unlock is immediate. One object can hold cold dust, hot plasma, and fast particles at once. Each layer announces itself in a different band. The oval ring is a dust torus. It is a dense belt of grains and gas. It blocks visible and ultraviolet light from deeper regions along many directions. It glows in infrared because the dust absorbs energy and re-emits it as warmth. The lobes are radio bright because fast particles spiral in magnetic fields. The X-ray cusp is hot gas or extremely energetic processes close to the core. These components are not separate objects, they are nested layers. The geometry is the guide. The ring has a sharp inner edge and a softer outer fade. The inner edge looks like a clean boundary. The outer fade is a gradient as if the ring feathers into a thinner veil. The lobes begin narrow near the core and widen with distance. Their edges are brighter than their interiors in places. This limb brightening hints at thin layers within the outflow. The next key is obscuration, the hiding of inner regions by intervening material. Obscuration is not only darkness, it is selective darkness. It removes some bands and spares others. The dust torus can hide the ultraviolet core while allowing radio waves to pass. It can also dim soft X-rays more than hard X-rays. This selectivity becomes a tool. A third scene settles on the ring in infrared light. The ring is not uniform. One side is brighter. The brighter side faces the inner source more directly. The far side is dimmer. The dimness is not distance alone. It is also angle and thickness. The ring is like a thick collar around a lamp. The collar glows where the lamp heats it. The collar stays cooler where the line of sight cuts through more material. The collar analogy is unique here and does not rely on any human setting. It matters because it turns a complex structure into a simple rule. Warmed dust glows, shielded dust stays cooler. The ring therefore encodes both geometry and heating. The third key is jets' narrow outflows that carry energy away from the core. The jets appear as radio lobes and sometimes as X-ray streaks. In this galaxy, the jets carve two channels. Each channel is narrow near the center and wider farther out. The widening suggests spreading and interaction with surrounding gas. A fourth scene forms at the base of one lobe. A bright knot sits along the jet. Ahead of it, the lobe edge becomes sharper. Behind it, the brightness is smoother. The knot marks a shock where flow changes. The shock compresses material and strengthens magnetic fields. The compression brightens radio emission. It can also heat gas to X-ray temperatures. The knot is a physical detail tied to a boundary. It is a local thickening within a long structure. Another small payoff appears. Knots show where a jet deposits energy into its surroundings. The jet is not a simple beam. It is a sequence of interactions. Each interaction leaves a bright imprint in at least one band. The scale shift becomes calm and clear. Near the center, the region is compact. It spans distances comparable to a solar system. Farther out, the lobes can extend across lengths comparable to a galaxy. The same outflow links the two scales. The ring sits between them. It is large compared with the core and small compared with the lobes. The nesting is the story. A fifth scene appears when the galaxy is imagined in X-rays. The central cusp is bright. Around it, a softer halo spreads. The halo is patchy. It has faint cavities aligned with the radio jets. The cavities are dimmer in X-rays because hot gas has been displaced. Around each cavity, a brighter rim appears. The rim is a thin shell where gas piles up. Another payoff lands gently. Different bands can confirm the same pressure structure. Radio reveals where particles and fields fill the cavity. X-rays reveal where hot gas is missing. The combination turns absence into evidence. A sixth scene settles in visible light. The host galaxy looks smooth. Dust lanes cross its inner region. The lanes align with the infrared ring. Yet the visible view alone cannot show the jets clearly. The jets are too faint in this band. They are also partly hidden by the ring. The visible view gives context and structure. The radio and X-ray views give the energetic anatomy. Together they show why multi-wavelength astronomy matters. It is not only about adding colours, it is about separating layers by their physics. Now the limit arrives quietly. The inner engine cannot be seen directly if obscuration is strong. A bright infrared ring can hide the central ultraviolet source completely. The energy output must then be inferred from reprocessed light. That inference depends on dust properties and geometry. Another limit comes from angle. A jet can appear bright or faint depending on its direction relative to the line of sight. Orientation biases what is seen. A third limit comes from blending. The core region contains many emitting zones at different temperatures. A single band can mix them into one brightness peak. Separating components requires multiple bands and careful modelling. Resolution is also a constraint. Faraway galaxies compress into small angles. Fine structure in the ring can blur. Knots in jets can merge into one smooth streak. The result can hide the true number of interaction sites. Even with limits, a stable portrait remains. The dust ring is a thick belt with a sharp inner boundary and a soft outer fade. The jets are narrow channels that widen into lobes with bright edges and dim interiors. The X-ray halo is a hot atmosphere shaped by cavities and rims. The radio haze is a broad envelope that holds the outer imprint of the jets. The whole system behaves like layered geology in the sky. Each layer records a different process. Each layer overlaps without merging. The next step follows how these layers change with time. Variability across bands will begin to act as a ruler for size and distance within the same object. Time itself becomes a wavelength when light rises and falls across different bands. A change begins near a compact core and then appears later in surrounding layers that absorb and re-emit. In a distant galaxy center, a small bright region pulses in X-rays. The pulse is brief and sharp. Around it, an infrared ring does not respond at once. The ring brightens after a delay. The brightening begins on one arc of the ring. It then slides along the circumference like a slow tide line. The first unlock settles in place. A delay between bands measures distance inside one object. Variability is the change of brightness over time. It can be fast in a compact region and slow in a larger one. Reprocessing is energy absorbed and released again as different light. It resembles a cliff face at dawn. The highest ledge warms first. The lower wall warms later and glows after the direct light has shifted away. The importance is direct. The sequence of brightening reveals which layer sits closer to the source. The compact X-ray pulse suggests a very small region where hot plasma changes quickly. The infrared ring suggests dust that responds more slowly. Dust grains absorb energetic light and raise their temperature. They then emit infrared light as warmth. The grains do not store heat for long in absolute terms, yet the signal from the ring is delayed by travel time. Light must reach the ring before the ring can glow. In that region, the delay is about a month, like the span of a lunar cycle. That number is not only a clock, it is a ruler because it ties the ring size to the speed of light. A second scene forms as the infrared brightening continues. The ring is not uniform. It has thicker segments. It has thinner gaps. Where the ring is thicker, the glow rises higher and then fades more slowly. Where the ring is thinner, the glow rises modestly and falls sooner. The brightness change follows a gradient around the ring. The gradient suggests uneven density. It suggests a layered belt rather than a perfect circle. Another small payoff appears. The shape of the response carries the shape of the material. A smooth ring would brighten evenly. A clumpy ring brightens in patches that linger. The ring becomes a map of dust distribution drawn by time. The same event can also appear in visible light, but in a different way. A faint halo around the core can brighten as scattered light increases. The halo is not a ring. It is a soft oval with a brighter inner boundary. Its inner boundary is sharp where dust is dense enough to scatter efficiently. It fades outward where dust becomes sparse. The boundary moves only in brightness, not in location. The brightness changes reveal a new clue. Scattered light can respond quickly because it does not require heating. It only requires illumination. The heating response in infrared can be slower and smoother. It depends on temperature change and on how deep the light penetrates into the dust. A third scene settles at radio wavelengths. The radio lobes respond much more slowly. Their brightness changes are subtle. The lobes are large. They carry energy far from the center. Their changes can take long times to propagate. The radio emission comes from fast particles spiraling in magnetic fields. Those particles can be replenished in bursts, yet the lobe size acts like a reservoir. It smooths sharp changes into gradual ones. This offers another unlock. The same central variability can look sharp in X-rays and almost steady in radio. The difference is not contradiction. It is a measure of scale. A compact zone can change in hours or days. A broad zone averages changes over far longer spans. The scale shift is gentle. An electron in hot plasma radiates in moments. A lobe spanning interstellar distances holds a history that stretches across ages. Now a fourth scene forms in X-rays again. The central pulse is followed by a softer X-ray glow that fades more slowly. The glow comes from a region slightly farther out. It can be a hot corona of plasma above a dense disk. It can also be a shock in a compact outflow. The details vary, but the timing remains useful. The harder X-rays peak first, the softer X-rays peak later. The sequence suggests a stratified region where temperature or opacity changes with radius. The physical detail is a layered gradient. The inner zone produces higher energy light. The outer zone produces lower energy X-rays. Another payoff settles in. A spectrum that shifts with time can show structure even when images are blurred. Timing becomes a substitute for spatial resolution. Yet the method has limits that remain calm and clear. The first limit is geometry. The ring is not a single radius. It can be thick. It can be warped. Parts of it can sit closer or farther along the line of sight. A measured delay then becomes a blend of many paths. The second limit is orientation. If the inner source is partly blocked by a dust belt, only certain directions receive direct light. The ring response then looks uneven. An uneven response can mean clumps. It can also mean shadowing. The third limit is contamination. Infrared light can include both reprocessed core light and unrelated warm dust in the host galaxy. Those components add together and soften the signal. The fourth limit is the finite speed of internal changes in the material. Dust heats quickly, but surrounding gas can respond with its own delays through ionization and cooling. If several processes overlap, the lag can be hard to assign to a single layer. These limits do not erase the method. They define the questions it can answer. Another scene settles into a calmer rhythm. Instead of one flare, the core flickers in a sequence. The X-rays rise and fall in short pulses. The infrared ring responds as a smoothed echo. Each pulse creates a small wave of warmth that travels along the ring. The waves overlap. Where they overlap, the ring stays bright. Where they do not, it dims. The result is a slow breathing of the ring that follows the faster breathing of the core. This offers a quiet certainty. Multi-wavelength timing can separate cause and effect. A rise that appears first in X-rays and later in infrared suggests heating and re-emission. A rise that appears first in optical scattering and later in infrared suggests illumination followed by warming. A rise that appears in radio only after long intervals suggests energy transport to distant lobes. The full portrait is not one picture. It is a choreography across time. The choreography is legible because light travels at a fixed speed. Yet the choreography remains gentle because the layers respond in smoothing ways. A final scene returns to the ring as the last glow fades. The bright arc becomes a dim arc. The dim arc becomes an even belt. The belt merges back into the host galaxy background. The central X-ray cusp quiets. The object appears steady again, but the stored record of timing remains in the sequence that has passed. From here, the spectrum can move toward another kind of hidden structure. The next step follows how light can be filtered by direction and orientation, revealing geometry through subtle changes in polarization and shadow. Some light carries a faint direction, as if a surface leaves a gentle signature. That direction, called polarization, reveals hidden geometry, when ordinary brightness looks smooth. In a young system wrapped in dust, an edge-on disk sits as a thin, dark band across a brighter haze. Above the band, a soft fan of light opens. Below it, a second fan mirrors the first. Each fan has a brighter rim and a quieter interior fade. The dark band is sharp in the middle and softer toward the ends. The fans are not centered on a point. They curve slightly like two slow wings made of mist. At this distance, light behaves as a sculptor of boundaries. The disk blocks direct light along its midplane. Dust above and below scatters light into view. The scattered glow carries polarization because scattering favors certain directions. Polarization is light with a preferred vibration direction, like tall grass leaning together under steady wind, like ripples that stretch longer in one direction than another. It matters because the preferred direction encodes how light turns at dust grains. A small unlock arrives quickly. A single scatter tends to produce stronger polarization than many scatters. Where the fan looks crisp and thin, the signature is cleaner. Where the fan looks thick and cloudy, the signature is mixed and weaker. The disk edge becomes more than a shadow. It becomes a ruler for how many turns light takes before escaping. Another scene settles along the brighter rim of the upper fan. The rim is brightest near the disk's center. It fades outward through a smooth gradient. The rim also narrows where the disk looks thicker. The narrowing suggests higher density there. Higher density means more scattering events. More events blur the preferred direction. The pattern links brightness and direction without any need for motion. A calm payoff follows. Polarization can distinguish a bright region made by direct illumination from a bright region made by many scattered paths. The first tends to keep a cleaner direction. The second tends to lose it. A single band of brightness cannot always separate those causes. Direction can. The scale shifts inward. Dust grains are smaller than a grain of sand. Their shapes are not perfect spheres. Their surfaces can be slightly elongated or layered. That small asymmetry matters. It lets grains scatter and absorb light unevenly. The scale shifts outward again. The disk spans a region large enough to hold many orbits. Yet the same microscopic grain behavior sets the large fan shape. Another scene forms when the same system is imagined in near-infrared light. The dark band stays, yet it looks thinner. The fans become smoother and extend farther. The rim brightness softens. Near-infrared slips through dust more easily. More light reaches deeper layers before it turns and escapes. Another small unlock settles in. If polarization remains strong in near-infrared, scattering is still dominant in the glow. If polarization drops while brightness rises, warm dust emission begins to matter more. Emission tends to be less polarized unless grains are aligned. The change between bands becomes a separator for mechanisms. A number enters quietly. In many dusty fans, polarization reaches about 10%, like one stream in 10 within a wide delta flowing in the same direction. The number is small compared with total light, yet it is large enough to carry structure. It offers a simple lesson. Direction can be a faint ingredient that guides interpretation. Now the visual anchor deepens. Along the fan, the preferred direction changes smoothly with position. Near the disk, it tends to align along arcs that wrap around the center. Farther out, it tends to fan outward. The change resembles a field of reeds that bends around a boulder, then straightens downstream. The boulder is the dense disk. The downstream region is the thinner halo. Another payoff appears. The curvature of the preferred direction reveals the three-dimensional shape of the scattering layer. A flat layer produces one pattern. A flared layer produces another. A warped layer twists the pattern further. Even when the disk is too small to resolve in detail, the directional pattern can imply its tilt and thickness. A limit arrives gently. Polarization is easily diluted. If bright, unpolarized light from elsewhere overlaps the fan, the signature weakens. If several layers scatter light with different angles along one line of sight, their preferred directions can cancel. The result can look nearly zero even when each layer is strongly polarized. The observation is therefore indirect. It measures a net balance, not a single clean layer. Another limit follows from multiple scattering. When light bounces many times, the memory of the first surface is lost. The fan can still glow brightly while direction becomes confused. A third limit comes from dust properties. Grain size and composition change the strength and wavelength dependence of polarization. Without multiband coverage, a weak signal can be misread as a geometrical effect when it is a grain effect. These limits define the boundary of what can be claimed. Within those boundaries, polarization still adds a stable dimension. It is not a picture of where light is, it is a hint of how light arrives. Another scene settles into a wider setting. A reflection nebula surrounds a dense core. The nebula is pale and blue in visible light. It is dimmer and redder in near-infrared. Its brightness is highest along a crescent. The crescent is a thin arc with a sharp inner edge and a soft outer fade. In the crescent, polarization is stronger than in the surrounding haze. The reason is simple. The crescent is dominated by single scattering off a curved surface. The surrounding haze contains light that has wandered through more turns. A quiet unlock follows. Polarization can pick out the cleanest scattering surfaces even when brightness looks continuous. Those surfaces trace cavities and shells. They outline where dust is swept into curved layers. Now the scale shifts again. The crescent arc can form over thousands of years as flows rearrange dust. The grain-level interaction happens in less than a heartbeat of cosmic time. The same physical rule connects them. Another scene forms in radio light from a broad lobe near a galaxy core. The lobe is smooth in total brightness, yet its polarization shows bands. Some bands run along the lobe edge. Some cross the interior in faint stripes. The stripes are not rigid lines. They are soft lanes. Their edges fade. They suggest ordered magnetic fields stretched by flow. Magnetic fields are not a separate object here. They are a property of plasma. The plasma guides particle spirals. The spirals produce polarized radio emission. A small payoff appears. Radio polarization can reveal the direction of ordered fields even where the plasma itself is invisible. It can show where a lobe is compressed at its rim. Compression aligns fields. Alignment strengthens directional signal. The rim becomes a boundary traced by direction rather than brightness. A limit arrives softly here as well. Faraday rotation can twist polarization as radio waves pass through magnetized plasma. The twist depends on wavelength and on the path's properties. If the path is complex, the net direction can be scrambled. The observation then becomes a mixture of source and intervening medium. Another limit is resolution. Fine bands can blur into one broad lane. Small twists can be lost. Yet the broad story survives. Directional information across bands traces layered physics. Visible and near-infrared polarization trace dust scattering and dust emission. Radio polarization traces ordered fields in plasma. X-ray brightness traces hot gas pressure. Gamma timing traces compact engines. When placed side by side, the bands do not compete. They complement. Each one answers a different question about the same shape. A final scene returns to the edge on disk. The dark midplane stays as a clean line. The fans keep their soft wings. The rim glow stays brightest where density and angle combine. Over time, the pattern shifts slowly as dust rearranges and illumination changes. The object remains calm. The added dimension of direction makes it deeper. From these directional hints, the spectrum can widen toward full inventories of matter and energy. The next step follows how multi-wavelength light builds a balanced accounting across long cosmic time. Some regions of the sky glow even when no single object stands out. Multi-wavelength light turns that glow into an energy budget with hidden ledgers. In a wide field around a dusty spiral galaxy, visible light shows pale starlight crossed by dark lanes. The lanes look like soft ribbons laid across the disk. Each ribbon has a sharp edge where opacity rises. Each ribbon has a gentle fade where dust thins. Infrared light shows a broad oval warmth that follows those same ribbons. The warmth climbs as a smooth gradient toward the center. Radio light shows a thin halo that extends beyond the disk into darker space. A quiet payoff arrives early. The same energy appears in different disguises because matter transforms light rather than only hiding it. Reprocessing enters as the first core idea. Reprocessing means absorbed light returns later at longer wavelengths. A dark lane in visible light is not a void. It is a place where energy takes a detour through dust. The lane casts a soft shadow with a crisp boundary on one side. That same boundary glows in infrared as a thicker band. The band holds a warm center and cooler edges. The two maps align without effort. Where dust grows dense, visible light fades. Where dust grows dense, infrared light grows stronger. Another small unlock follows. The lane looks like absence in one band and like presence in another band. The mechanism stays physical and plain. Dust grains intercept starlight and warm slightly. The warming is steady across countless grains. That steady warmth becomes a broad infrared glow. A second slow scene settles within the spiral arms. In visible light, the arms carry patchy knots with bright rims. The rims mark sharp transitions from clear to dusty regions. The interiors look mottled where dust scatters and absorbs. In infrared light, the same arm becomes smoother. It looks like a continuous ribbon of warmth draped along the curvature. A simple payoff lands there. And infrared light sums many small sources that visible light breaks into pieces. Hidden activity becomes measurable as total heat. A single number enters and stays calm. In many galaxies, about 1/2 of starlight is absorbed by dust and re-emitted in infrared light. That is like 1/2 of a stream that slips underground and reappears nearby. The fraction is not identical in every system. It rises when dust is thick and clouds are crowded. It falls when clearer paths open through the disk. Yet the presence of a large share changes what counts as brightness. A galaxy that looks modest in visible light can still carry strong power in infrared. Another scene leans closer to the midplane. The dust ribbon is darkest near the center. The infrared band is brightest in the same place. The edge of the ribbon looks like a boundary drawn with charcoal. The infrared rise looks like a soft lamp behind thin fabric. The physical detail matters. The boundary is where dust optical depth changes quickly. The gradient is where dust temperature and density change slowly. The main visual anchor widens beyond the single spiral disk. A diffuse background fills the field in long wavelength light. It is not uniform. It has a soft grain like calm fog against a dark hillside. The fog is not located at one distance. It is the sum of countless faint sources layered along depth. Some sources are dust rich and bright in infrared. Some are clearer and contribute more at shorter wavelengths. The grain is gentle. Slight bright patches sit beside slight dim patches. The patterns suggest clustering without sharp edges. A payoff arrives with the fog. Background light is a census that counts energy even when individual contributors are too faint to isolate. This census does not need a bright starburst to matter. It adds up quiet galaxies across enormous distances. Another slow image accompanies that idea. The fog thickens a little near crowded regions. It thins a little toward emptier ones. The changes are small but persistent. The field behaves like layered haze with subtle ripples. Redshift enters as the second core idea. Redshift is the stretching of light to longer wavelengths by expansion. It behaves like ripples that widen as a pond grows calm. It behaves like a pattern on cloth pulled slowly at the ends. Light that begins blue arrives less blue. Light that begins visible can arrive as infrared. A glow once in ultraviolet can slip into longer bands. Time becomes a gentle colour shift. Another payoff settles in. Long wavelength background light is not only nearby dust, it can be ancient light shifted into a different band by the growth of space itself. This shift also creates a soft ambiguity. Infrared light can mean warm dust close by. Infrared light can also mean distant starlight stretched into the same region. A slow scene forms in the spectrum itself. Brightness rises and falls as wavelength changes. In shorter bands, one broad rise belongs to direct starlight. In longer bands, a second broad rise belongs to dust emission. Between them sits a boundary zone where the curve turns over. The boundary is a physical clue. It marks where energy stops escaping directly and starts returning as heat. Another small unlock appears. The relative height of the two rises shows how much power is direct and how much is reprocessed. The position of the infrared rise hints at dust temperature. Hotter dust shifts the rise toward shorter infrared. Cooler dust shifts it toward longer infrared. The curve becomes a quiet fingerprint. It is not a name or a label, it is a shape that carries the budget. A limit of observation arrives without tension. The same infrared brightness can be made by a small mass of hot dust or a larger mass of cooler dust. Brightness alone cannot separate those cases. Several infrared bands are needed to outline the curve. For very faint sources, the curve can be undersampled. Another limit follows from mixing along the line of sight. Background light adds together many sources at many distances. Distinct eras overlap in the same band. A small bump in the spectrum can hide several populations beneath it. This census remains real, yet the details can blur. This is the boundary of inference. The budget can be estimated robustly. The exact split among contributors can remain uncertain. The scale shift becomes calm and wide. Inside a dust grain, absorbed energy becomes heat in less than a moment. Inside a cloud, dust warms and cools as the radiation field drifts. Inside a galaxy, spiral structure rearranges clouds over long ages. Across cosmic history, the same detour through dust shapes the background over immense spans. The process repeats across scales without changing its nature. A final scene returns to the spiral galaxy as the field quiets. The visible starlight dims first behind the dust ribbon. The infrared band remains as a gentle glow. The diffuse background fog persists with its soft grain. The next section follows how this budget tilts in crowded regions and in emptier voids. The same accounting holds, yet the balance shifts. A galaxy cluster can seem like a quiet gathering until heat and gravity sketch its true structure. Multi-wavelength light reveals where mass sits, where gas is pressed into shocks, and where cooler material still hides. In X-rays, a broad glow fills the space between many galaxies. The glow is smooth near the center. It fades outward through a long gradient. Along one side, a sharp arc cuts across the haze. The arc looks like a thin rim with a brighter edge and a dimmer interior. At this distance, light behaves as a tracer of pressure. The sharp arc marks a shock front in hot plasma. The hot plasma is gas-stripped into free particles. It shines in X-rays because particles slow and release energy. The first unlock arrives without effort. A bright X-ray glow points to hot gas even when stars look calm. The hot gas is not a minor detail. In many clusters, it holds more normal matter than the galaxies themselves. A second scene settles on the arc-shaped rim. The rim is thin. Its boundary is clean. Just behind it, the glow thickens like a layered shell. The shell has a gentle interior gradient. The edge stays crisp because density changes quickly there. The interior stays soft because temperature and density vary slowly. The physical detail is a boundary that behaves like a wave frozen in place. The shock is a moving surface, yet it appears as a stable arc at one moment. A small payoff follows. The thickness of the rim hints at how sharply energy is deposited. A very thin rim suggests a sudden jump. A broader rim suggests mixing and spreading behind the front. Radio light adds a new layer to the same arc. In radio, a faint crescent appears at the cluster outskirts. It follows the same curvature as the X-ray rim. The crescent is brighter along its outer edge. It fades inward like a veil pulled thin. The crescent is a relic arc made by fast particles spiraling in magnetic fields. The particles are energized at shocks and stirred by turbulence. The second unlock settles in. Radio traces motion and magnetism where X-rays trace heat and pressure. The two arcs together show that the shock does two jobs. It heats gas and it accelerates particles. The cluster begins to resemble a sand dune under steady wind. The dune edge is sharp where grains pile up. The slope behind it is smooth where grains settle. The analogy stays gentle and grounded. The wind is gravity-driven flow through a cosmic landscape. The grains are particles and fields responding to compression. It matters because it turns a complex plasma into a simple shape rule. Compression sharpens edges. Relaxation smooths them. Now visible light enters with restraint. The galaxies appear as small ellipses embedded in the cluster. Some are pale and smooth. Some show dust lanes as thin, dark threads. The cluster core looks crowded, yet much of the space between galaxies is dark in visible light. That darkness is not emptiness. It is simply gas too hot to glow in those wavelengths. Another payoff arrives. Different bands prevent a false intuition that only stars matter. Heat can dominate the volume and still stay invisible to visible light. Infrared light adds a quieter whisper. In infrared, a few galaxies shine with soft warmth. The warmth often aligns with faint dust bands and compact cores. Cooler dust can glow in infrared even inside a harsh environment. The warm points are not the main cluster glow. Yet they reveal that some cold material survives. This is a third unlock. A cluster can hold extremes side by side. Hot gas fills the volume. Cooler dust persists inside dense pockets. The scale shift becomes calm. A dust grain is smaller than a grain of sand. A dust lane spans a galaxy. A cluster spans many galaxies. The same absorption and re-emission physics operates at every step. Now gravity itself becomes visible through a subtle distortion. Light from more distant galaxies passes through the cluster. The paths bend slightly. Some background shapes stretch into faint arcs. Some stretch into gentle shears. The arcs are not bright. They are delicate curves around the cluster core. They trace where total mass bends space-time. Another small payoff settles in. Gravity can map mass even when the mass does not shine. The bending responds to everything that gravitates. It does not care whether matter is hot, cold, bright, or dark. This creates a powerful pairing. X-rays show where hot gas sits. Gravitational bending shows where total mass sits. Where the two align, hot gas follows the deepest potential wells. Where they offset motion and mergers are at work. Another scene returns to the sharp X-ray rim. The rim is not centered on the galaxy distribution. It sits off to one side. The offset suggests a recent collision between subclusters. Gas can slow and shock. Mass can pass through with less drag. The cluster becomes a layered system with different rules for different components. The gas is collisional. It feels pressure. The mass traced by bending is mostly collisionless. It follows gravity with minimal direct interaction. The next payoff arrives gently. Multi-wavelength separation allows the components to be compared without confusion. A cluster is not one substance. It is several substances sharing one gravitational stage. One number enters and stays simple. The hot gas often reaches about 10 million degrees, like the hottest part of lightning scaled far beyond any storm. The comparison is only a guide to extremity. The exact value varies by region. Near the shock rim it can be higher, in cooler pockets it can be lower. Yet the order of magnitude is enough to set intuition. At 10 million degrees, atoms are stripped. The gas becomes a plasma. That state explains why X-rays dominate its emission. Another visual anchor settles deeper into the cluster core. The X-ray glow there is brighter and rounder, yet it is not perfectly smooth. A faint edge appears like a cold front. The edge is a curved boundary where denser cooler gas meets hotter surroundings. The boundary stays sharp because mixing is limited. The interior side is brighter because density is higher. The exterior side is dimmer because density drops. Another payoff follows. A sharp edge in X-rays can mark motion even without any visible displacement. The edge is a pressure-balanced surface shaped by flow. The flow is not seen directly. The boundary reveals it. Now the limits of observation arrive softly. X-ray brightness depends strongly on density. Very tenuous gas in the outskirts can be hard to detect. A faint outer halo can vanish into background. The result can hide where the cluster truly ends. A second limit appears in the gravity map. Bending measures mass projected along the line of sight. Separate structures at different distances can overlap. The arcs can therefore reflect a stacked sum rather than a single layer. A third limit comes from band mixing. Radio relic arcs can be faint and patchy. Some shocks may heat gas without producing strong radio emission. Some radio features may persist after the shock has weakened. Timing is not always available at these scales. The comparison between bands is therefore a careful inference. Even within limits, the combined view holds steady. X-rays reveal the hot atmosphere and its shocks. Radio reveals the energetic particles and magnetic shaping at the same boundaries. Infrared reveals surviving cool dust pockets in some galaxies. Gravity reveals the underlying mass skeleton. Together, the cluster becomes a calm demonstration of how each wavelength answers a different question. Heat answers how gas is compressed and stirred. Radio answers where particles gain energy and where fields align. Infrared answers where cooler material persists. Gravity answers where the deep structure sits even when it does not glow. The scale shift widens again. Widens. A shock front can span hundreds of thousands of light years. The same front forms from particle collisions that occur over microscopic distances. The cluster holds those extremes without strain. The arc in X-rays is a boundary in a sea. The crescent in radio is a thin veil along the same curve. The faint gravitational arcs are gentle ripples from deeper geometry. The final scene lets the cluster quiet in imagination. The outer rim fades into darkness. The inner glow stays like a steady ember. The relic crescent softens and blends into the radio haze. The gravitational arcs remain delicate and still. From here, the last section can release tension entirely. The spectrum can return to a soft landing that keeps only the calmest truths. The sky settles into calm when every wavelength is allowed to speak at once. Multi-wavelength light does not add drama, it adds balance. In one quiet region, a hollow bubble of gas hangs in interstellar space. The bubble has a thin rim like a pale ring. The ring is uneven. It thickens in some arcs and thins in others. The interior looks darker in visible light. The rim looks brighter where dust gathers into a soft boundary. At this distance, light behaves as a layered story. Some layers show what glows, some layers show what blocks. The first unlock comes early. No single band tells the whole truth because matter is not equally transparent to every color. Transparency is the first core idea. Transparency means a medium lets some wavelengths pass with less loss. Dust grains block much of visible light. The same dust lets many radio waves pass. The difference is not subtle. The same region can look empty in one band and full in another. A slow scene forms along the rim. In visible light, the ring is traced by faint scattered glow. The glow has a sharp outer edge. The edge fades inward through a gradient. The gradient shows dust thinning toward the cavity. In infrared, the same rim becomes warmer and broader. The warmth is smooth like a thin cloud band. It follows the curvature with little break. Another payoff arrives. The rim is not merely outlined. Its thickness becomes readable because heat spreads through many grains. The bubble interior shifts the focus next. In X-ray light, the cavity is not dark. A dim haze fills the hollow volume. The haze is brightest near the center. It fades outward as a gentle bowl. The bowl is a pressure hint. Hot gas fills the cavity with low density. The gas does not need to be seen in visible light to exist. A new unlock settles in. Empty and full are not opposites in space. They are labels tied to wavelength. The second core idea enters with restraint. Layering means different bands isolate different physical components. Radio often traces cold gas motions. Infrared often traces warm dust. Visible light often traces direct starlight and scattered light. X-rays often trace very hot plasma. Gamma rays can trace rare high-energy interactions. The bubble rim carries all of these in different proportions. The rim is a boundary where conditions change quickly. Inside the rim, density drops. Temperature can rise. Magnetic fields can drape along the shell. A slow, visual anchor rests on that drape. Along one segment of the rim, radio brightness forms a thin filament. The filament is narrow. It runs like a seam along the arc. Just outside it, radio fades. Just inside it, radio also fades. The seam suggests a field aligned and compressed. Another payoff appears. A thin radio seam can mark where charged particles spiral most efficiently. The seam can be present even when visible light stays quiet. The scene widens beyond the bubble. A broader background glow lies behind it in long wavelengths. The glow looks like faint fog with subtle mottling. The mottling has no sharp boundaries. It looks like slow waves in haze. The glow is a sum across depth. Some parts are near, some parts are far. A gentle unlock follows. Background light is not a single place. It is a layered accumulation. Here the primary analogy arrives and remains singular. The spectrum resembles tide lines on a quiet shore. One tide line sits high and faint. Another sits lower and darker. Each line marks a different reach of water. Each wavelength marks a different reach of physical conditions. The shore does not change its identity. Only the marking changes with the tide. The bubble rim holds several such marks at once. One number enters and stays simple. About 3 broad layers often dominate the reading of such a region. One layer is direct light that escapes. One layer is dust light that returns after absorption. One layer is hot gas light that emerges at higher energies. The 3 layers are like 3 tide lines. They are distinct yet connected. The connection is energy and matter. A small payoff follows that number. When the 3 layers are compared, the energy budget becomes stable even if details blur. A limit of intuition arrives softly. A bright infrared rim can mean more dust. It can also mean warmer dust. Without enough wavelengths, the two cases mimic each other. The curve can be undersampled. Another limit appears with longer wavelengths. Long waves smear fine edges. A wave that is large cannot outline a tiny knot. The rim can look thicker than it is. A third limit follows from overlapping depth. Foreground and background can align by chance. A single bright patch can hide two separate structures. The layered reading remains useful. It simply carries uncertainty in the split among layers. The bubble interior returns to the center of attention. In X-rays, the haze suggests heat, yet the exact temperature is hard to pin down from brightness alone. The brightness depends on density as well as temperature. A gentle payoff arrives. Even without exact values, a cavity glow signals that energy exists in gas rather than dust. The rim then offers a calm contrast. In visible light, the rim edge stays sharp where dust is thick. In infrared, the rim glow spreads wider where dust is warmer. In radio, the seam stays thin where fields align. Each band prefers a different geometry. Edge gradient seam bowl. These shapes are the quiet vocabulary of multi-wavelength light. A scale shift enters and stays gentle. A dust grain responds to radiation in moments. A shell responds to pressure over long ages. A bubble can persist for millions of years as it expands and thins. Over deeper time, countless shells overlap and fade into the background haze. The same physics repeats. Absorption and re-radiation, compression and alignment, transparency and blockage. Another slow visual anchor forms as the rim dissolves outward. The ring becomes patchy. Small gaps appear where dust has thinned. The infrared glow bridges some gaps. The radio seam breaks into short segments. The X-ray bowl remains smooth. The mixed view creates a final quiet unlock. Continuity is not always in the sharpest band. Sometimes the most stable structure is the faintest haze. The end approaches without a new mystery. The bubble is one scene among many. The point is not the bubble alone. The point is the method of calm comparison. A wavelength is a question. What passes through? What warms? What shocks? What aligns? What accumulates over depth? When those questions are asked together, the sky becomes less ambiguous. The rim stays a rim in every band. The interior stays a cavity in every band. Only the meaning changes with color. The last image rests on the full spectrum as a single quiet field. The haze is soft. The boundaries are readable. The gradients are slow. In that steadiness, the story can taper and remain at rest.